Hello, and welcome to another edition of our chemistry PowerPoint lectures. Hoping to make this one a little quicker than last one. I think it works better if you've watched the acids and base one, or if you read the chapter on acids and base one. This one is called What is pH? And the purpose for this one, I hope it's short and sweet, but gets to the point, is for you to understand what pH is, where we got it from, and why the numerical scale on pH works the way it does. This first slide right here basically is a slide we had from my last presentation on acids and bases. That one talked about properties of acids and bases, the pH scale, it introduced it, and strong acids, strong bases, reactions of base. There was a bunch of stuff on acids and bases. This one we're going to just focus on pH. So we learned that the pH is a scale that shows how acidic or basic something is. Second bullet point here says that neutral substances that are neither acids nor bases have a pH of 7. And this is why I made this PowerPoint. Some people ask me, Mr. Angulo, why did they make neutral substances pHs of 7? Why is 7 the middle? Why not 5? Why don't you make pH a scale of 1 through 10 and 5 be the middle? Or why don't you make it from 0 to 100 and 50 be the middle, right? Water could be a pH of 50. It turns out that the numbers that we're using on the pH scale they're not like ratings like on Yelp or some of the customer ratings or scores from a figure skating or gymnastics competition. These numbers are actually numbers that have been calculated. pH has to do, and I'm going to look at the equation. We're going to look at the equation for pH in just a little bit, but it has to do with orders of magnitude or exponents of concentrations. So this is what actually the pH ended up being. Nobody chose neutral pHs to be 7. They ended up being that once we calculated pHs. So we saw earlier, acids have a pH of less than 7. Bases have a pH greater than 7. So let's go on. And we saw this, the pH scale has, a bunch of acids and bases throughout the pH scale. 7's right here, pure water's right here. I saw this on the last presentation, and all these things are considered acids. Milk is slightly acidic, all the way down to, beer being 4.5, being acidic down here, vinegar way down here, lemon juice and stomach acid down there. Bases are over here. Baking soda is just slightly basic. Human blood, baking soda, bleach, and lye or sodium hydroxide being way over here, 14, right? So the scale is 0 to 14. Here, pure water is 7 right in the middle. Where does that 7 come from? It comes from the fact that pH, the definition of pH, is the negative log of the hydrogen ion concentration. And some of you guys may have used logs already. Usually you learn logs in Algebra 2. Some of you may have not. It's hard to do this class, this pH in chemistry class early in the school year, because even if Algebra 2 classes are going to go over logarithms, they're going to go over them at the end of the school year or close to the end of the school year. So I usually don't have much success in going over pHs at that time of year. Still, some of you guys haven't had logarithms, so it gets a little kind of confusing. But basically, when you're taking a logarithm of something, basically what you're saying is, for the hydrogen concentration, what is the exponent of the hydrogen concentration? In other words, we can rewrite this going, the hydrogen concentration is going to be, and I have this in another slide over here, but it's equal to 10 to the negative pH. So really your pH is the exponent of the concentration of hydrogen, right? So if the hydrogen concentration of a solution, let's say you have an acid solution that produces a concentration of 1 times 10 to the negative 4, then if you take this number right here and you plug it into this equation and you take the logarithm of 1 times 10 to the negative 4, really what you're going to get is the logarithm of 1 times 10 to the negative 4 is negative 4. That's what that is. It's the exponent. And so you're going to take the negative logarithm of that so that you don't, pH is in the negative, it's a positive. So for a hydrogen concentration of 1 times 10 to the negative 4, pH is just 4.0. Okay. Now let's say your concentration of hydrogen in another solution, let's say you have another solution, and that's a plus. That's equal to, the concentration is equal to 1 times 10 to the negative 3. And here I want to remind you that 1 times 10 to the negative 3 molar, I forgot to put that these are in moles per liter, is 10 times greater than 1 times 10 to the minus 4, right? Because this one is less negative, so it's bigger. If I plug it into the equation, if I just go ahead and take my calculator and there's a log button, there's a button in there that says log. If you put this number in and take log, or sometimes you have to put log in and get this number. If you plug that in, you're going to get that your log is 10 to the negative 3. So therefore, your pH is going to be equal to 3.0. So the pH really is related to this number up here. Okay. But not just that number, it's also kind of the number in front also. But I'm giving you kind of a guideline of where these pHs are. So the pH really these pHs have to do with the exponents, the powers of the concentrations. So a pH of 3 is going to be 10 times more concentrated than the pH of 4 in hydrogen ions. This number is 10 times more concentrated than that one. That's why when we looked at this scale right here, every pH number between 3 and 4 is 10 times greater. Okay. Now, if you have a concentration somewhere in between here, like your hydrogen concentration is, let's see, a number between 1 times 10 to the minus 4 and 1 times 10 to the minus 3. Let's say we're at right in the middle. Oops, that's supposed to be a 5. 5.0 times 10 to the negative 4. Okay. This is the number right between these two, right? 5 times 10 to the minus 4. So now you would think that it was 3.5, but it isn't, because logarithmic functions are not linear. They're logarithmic, which makes it a little different. But if I take my calculator and I plug in the log of 5 times 10 to the minus 4, and I get an answer, it ends up being, I get a pH of negative, well, the answer for the logarithm of this is negative 3.30. So since my pH is the negative of that, the negative of negative 3.30, I get the pH is positive 3.30. Okay, so that's where we get pH. It's not a made-up number. We didn't just say, hey, let's make 7 the middle. It kind of worked out that way. It worked out that when you have water by itself, the concentration of hydrogen ion, if you have this perfectly cool, crystal clear, pure glass of water, you never just have water in it. There is a dissociation reaction going on in water. And it's an equilibrium. I don't have a reverse arrow on this one, but it's an equilibrium reaction. And if you calculate what the concentration of hydrogen and hydroxide are in just a pure glass of water, it turns out that they are both 1 times 10 to the negative 7. So the hydrogen concentration, that's H plus concentration, is 1 times 10 to the negative 7. Okay, and how do we get that? Because the K for this reaction, we'll call it KW. KW. You'll notice that this is liquid. So the law of mass action for this is K is equal to hydrogen concentration times hydroxide concentration. Turns out it's 1 times 10 to the minus 14th. So if you're making, if you just had pure water right from the beginning and no hydrogen, no hydroxide, and you're making hydrogen ion, you're going to make an equal amount of hydrogen as hydroxide. So this one, this concentration here is going to be X. All right, we don't know what it is. We'll call it an X. This one's also got to be the same, so it's X. X times X is 1 times 10 minus 14th. Take this, X times X is X squared, takes the square root to get X, and the square root of 1 times 10 minus 14th is 1 times 10 to the minus 7. That's how you get that. Okay, so this is where pH comes from. It comes from this definition right here. We have this definition. And so pH is a number that is calculated. Nobody looks at lemon juice and goes, oh, that looks like a 2.2 pH. No, you actually take lemon juice, you measure the hydrogen ion concentration in it, and then you plug it into this this formula, and that's what you get your pH from, right? So that it turns out 7 ended up being what the hydrogen concentration was in pure water. And everything else also gets calculated from there. Okay, so yeah, we saw this before. Acids dissociate. And so this is the equation we use. If you want to find, if you're ever given a pH and you want to find out the hydrogen concentration, this is, if you haven't done logarithms, you wouldn't understand how you got this, but in order to solve for hydrogen concentration, you have to take what's called the inverse log, and the inverse log function will give you that hydrogen concentration is 10 to the negative pH. Really, that's kind of the way it works. For you guys who did know how to do it, you move the negative to the in front of the negative front of the pH, so you end up with log of H plus equals to the negative pH. Then take 10 to both sides, the log and the 10 to the canceled out, giving you this equation right here. All right, so that's where all that came from. I don't really want to go into much more details. Unfortunately, we ran out of time. I normally at this point have students actually calculate several pHs. Then we figure out acids. Using the equilibrium constants, we figure out how much hydrogen you're going to get from a dissociating acid. Then once you figure out the hydrogen, you plug it into this equation. That gets you your pH. But we're out of time. School year is just about done this week, and I guess we would need at least half week to do this. So I hope this has been helpful, at least clarified where it came from. We really didn't go into doing all the problems, but at least clarified where the pH came from and why the middle of the pH scale is 7 and not something a little bit more what we're used to, 5 or 10 or 50 out of 100, et cetera, and so on. Okay, all right. With that, I am signing off for this PowerPoint and possibly for the school year. If I don't talk to you anymore, have a great summer.